So, for spontaneous reactions, we want to do what? We want to minimize energy and maximize entropy. And so energy, we're talking in terms of delta H, but entropy, let's go on. So, when we determine entropy, entropies can be measured experimentally. And how are they measured experimentally? Well, what you do is you collect a whole bunch of heat capacities, C's. Heat capacities over a range of temperature. And so it's just a whole bunch of calorimetry experiments, right? If you do a whole bunch of calorimetry experiments, then we're going to collect data, like the heat capacity of a solid. Let's just look at water as an example, H2O. Solid ice, does it have a very high heat capacity? No. So the heat capacity, and the lower the temperature, the lower the heat capacity. And so the heat capacity increases somewhat until you hit 273 Kelvin. At 273 Kelvin, what's going to happen? Yeah, it liquefies, it melts, and then there's going to be a big jump in heat capacity, right? Because water has a fairly high heat capacity. This is quite important. And so, then once we go to steam, what happens to the heat capacity? And so, yeah, it'll drop back down, so about 373 Kelvin. And so since the heat capacity drops back down, does that mean that steam has a lower entropy than liquid water? No, actually steam should have a higher entropy than liquid water, right? And so it's not just directly proportional to the heat capacity. In fact, what it is this. Although you aren't going to measure, you can measure heat capacity. It's pretty close to 0 Kelvin, but not all the way to 0 Kelvin. But we can use the third law. At 0 Kelvin, what do you expect for the heat capacity? Zero. I mean, there's no way to absorb energy because everything has a fixed position, right? Everything has to be in its proper place. And so you can extrapolate this to 0 using the third law of thermodynamics, basically. But the trend is going to be this, and then there's this big jump up here, and then a big drop down, and then across here. And so what entropy is, experimentally, it's the area under this curve. And so, for example, if you want the entropy of water at this temperature, what you'd have to do is you'd figure out the area from 0 to T underneath the curve. If we want the entropy of water, liquid water at this temperature, then we just continue. Determine the area, etc. The entropy of gas is going to be much higher because if you look, it's the area it's taken from 0 to whatever temperature you have of interest. Okay. And so these are the ways we can determine. But so essentially, you can get the entropy at pretty much any temperature you want, right? And so if we're thinking about water, well, how many entropy values is that? A lot. A lot of entropy values, which becomes a bit of a pain. And so really, if you want to know one entropy value for water, what do you think the most useful temperature to know at? 25 degrees C, so that's what we'll do. This is going to be here at, what is it, 298, about a quarter of the way out. And so we want to know the entropy at 298. And so this would be called the absolute entropy at 298 Kelvin. Area under that curve. The absolute entropy. Well, those can be found in Appendix D. So let's take a look at Appendix D.
And it's broken down by elements, alphabetical here. So water, what would that be under, hydrogen or oxygen? Let's take a look, it's under hydrogen. Here it is. And so if we look at the entropy of water, it's the last column. Or, no, it's not the last column. One of these two. One of these is the heat capacity. The other is the entropy. Let's see which one it is. The last column is the heat capacity. What does this little P stand for?
Under constant pressure.
Under constant pressure. So this is heat capacity under constant pressure. Joules per mole Kelvin. This is entropy here. Joules per mole Kelvin. Let's take a look at the water here. H2O liquid has an entropy of 6991 joules per mole Kelvin. That would be the area. 6991. And so what we want to do when we have a table, what do you want to do if you have a table?
Look at it.
Yeah, you want to look for the biggest value and the smallest value. So let's look for the smallest value of entropy. Ooh, here, look at this one. Minus 99.6. Well, let's just look at one page. I don't want to. Oh, there's even a lower one. Minus 315.9. Minus 315.9. So if you see an entropy of minus 315.9, what do you visualize? Minus 315.9 joules per mole Kelvin.
There's less disorder.
There's less disorder than what? You should have some kind of reference point fixed in your mind. Less disorder than water, liquid water.
Much less.
Much less. What does a negative mean? Does that mean we're in an anti-universe? Something like that? What does a negative mean? That means that rather than going in from the disordered, we should be thinking about the order. Flipping? Just less disorder. Well, you know, it's like temperature. What does a negative 10 degrees C temperature mean? A negative 10 degrees C temperature just means it's colder than 0 degrees C, right? It doesn't mean that things start going backwards, right, as far as kinetic energy goes. It's still. And so that's our reference point there. And so this just means it has a lower entropy than water, and it has a lower entropy than 0, right? Or H plus, if you saw that. But we have to think in terms of absolute scale and relative scale. You know, if you have absolute temperature, can you have a negative temperature? You can't have a negative. 0 would be the coldest temperature, right? But a relative temperature like Celsius, you could have negative temperatures. And so what's going on here? Because what was the third law of thermodynamics again? Third law of thermodynamics is well, yeah, a perfect crystal has an entropy, absolute entropy of 0. You know, a perfect crystal, there's only one way to arrange that. You look at the Boltzmann equation. A perfect crystal is going to be 0. Perfect crystal is going to be 0. It's going to have the lowest entropy, right? It's going to be the most ordered, the most restricted, most constrained. And so what happens when it goes negative? Does that mean it's more ordered than a perfect crystal, true or false?
False.
So then what does it mean? Somebody explain to me what the negative means.
Is it a relative or hypercritical?
Yeah, okay. Omar remembers. Omar remembers that Appendix D is actually multiple tables wrapped up in 1, right? And so when we compare, if you notice, this one is for the ion here. These are things you notice. Okay, after you put in the biggest and the smallest, then you look for patterns in that. And you notice all the negative entropies are for, although this is solid, that's weird. These negative, this might be an error. But these ones are for ions. And so we saw the same thing. We saw the same thing with here. Good place to stop. We saw that hydrogen, H2 and H plus have the same delta H of formation, but they aren't the same, right? This 0 does not mean the same thing as this 0. You guys remember this from, or not? Remember? No, you don't remember this? In order to form H plus, there's got to be energy involved. Why are they calling it 0?
It's the sum of the reaction. I mean, it's such a long the sum of it is.
Well, you guys remember formation reactions? This one we could call like an absolute 0 because this is formation of 1 mole of H2 from 1 mole of H2. This one is an arbitrary 0, like Celsius, because we're forming 1 mole of H plus from half a mole of H2 gas. If we go from half a mole of H2 gas to 1 mole of H plus, this is going to cost energy, one way or the other. And so this is impossible to be 0. Why was it arbitrarily set at 0, like the Celsius? Somebody remind me. Why was it set at 0? You see, this is why it's good to once in a while to go back through, because it's easy to forget this stuff, right? It's so easy to forget. But then you might need it, if you're taking some kind of standardized test. I know there's some people who are planning to take things like the MCAT, but if I were planning to take the MCAT, I'd be flipping back through. Flipping back through the notes once in a while so it doesn't fade from memory. I don't know, I talked about this like 3 or 4 times, maybe even 5 times last semester. Had to do with, we use HCl as the example. Had to do with delta H of formation of HCl. No. Well, anyway, if we're forming, take a look at HCl. The delta H of formation of HCl is minus 167.2. What do you think the delta H of formation of just chloride is? In other words, how much of this 167.2 belongs to the formation of H plus, and how much of it belongs to the formation of chloride from the elements in their standard state? All of it belongs to chloride and none of it belongs to H plus? Could that be true in reality? No, but it's arbitrary because it's too difficult to separate, right? What is it, an 80-20 split, 20-80 split, right? And so you guys have to remember that for using Appendix D. When we use Appendix D, the same thing happens with entropy. For example, if we form an iron 3, we also have to have if we form a cation, we must also have a anion. And so how much of that heat capacity is due to the cation? How much of it's due to the anion? Is that an easy thing to measure? Can you put one probe for the cation and one probe for the anion and measure the difference in heat? No. And so the easiest thing to do is to set the arbitrary 0. And here you see it. Here are the 3 are now. Okay, delta H of formation, right? This was delta G. Actually, we haven't talked about delta G. And this is entropy. Do you think 1 molar H plus AQ at 298 Kelvin has 0 entropy? No, definitely not. And so this is arbitrary 0. And then everything's relative to that. And so what I mentioned in Chem 1A is that we have 3 tables here. We have a table for the compounds, we have the table for the cations, and the table for the anions. So you can compare cation to cation, anion to anion, right? But you don't want to cross-compare cation to anion or whatever. And so which one has a lower entropy? Let me ask you, which one do you think has a lower entropy? A perfect crystal, which has an entropy of 0, or iron 2 plus 1 molar, 298 Kelvin, which has an entropy of minus 137.7. Which one has a lower entropy? Perfect crystal. Right? That should be obvious, is it? Even though minus 137.7 is a smaller number, a lower number, isn't it? Okay. All right, so this is what you do when you go through the tables. You look at certain patterns, you look at these. One of the other patterns you'll notice is solids typically range from what to what. You know, so if we look at solids, solids typically have, look at iron solid, 27.28. 27.28 is kind of low entropy, right? FeCl3, 92.9. And so solids, you'll see, typically have entropies that range from, why is this FeCl3? That's odd. That have entropies that range from 0 to about, not 200, a little over 100. Maybe, you know, I'm just saying the typical range. And so if you look at, and you could, you know, the best thing is just to look for yourself. You know, to be told something, you know, somebody tells you, memorize this. You know, it's not very effective if you can come up with your own pattern, you know, that you've seen yourself. But solids are typically 0 to 100. Liquids are 100 to, and gases, well, yeah, over 200. Look at these gases here. Let's see. Gas, 250. Gas, 250. Gas, 260. Aqueous. Well, that's an ion, so we shouldn't compare. Gas. Oh, that gas is kind of low, 180. And so what we see is we see typical things. And when you look at water, water at 6991 is a liquid, but that has a fairly high entropy or fairly low entropy? Fairly low entropy. So why would you say water has a fairly low entropy at about 70?
About the value of a solid? It's about the value of a solid?
It's about the value of a solid, you know. Not the most ordered solid, but, you know, aluminum's pretty low. So let's see if we have other solids here. Copper solid, 3315. This is very low entropy here. Copper 2 oxide, 4263. This has a much higher entropy. This is a mix, copper 2 carbonate, copper 2 hydroxide. This has a fairly high entropy. Okay, copper 2 sulfate dot pentahydrate. And so why do you think water has a fairly low entropy? Compared to other liquids? What kind of bonding? Hydrogen bonding. Yeah, hydrogen bonding keeps the water molecules oriented, certain configuration, or tries to keep the water molecules oriented, which means that it's more ordered. If there was no hydrogen bonding interaction, then they're unconstrained. They can be in any orientation they want, but when there's hydrogen bonding in it, it's like a little magnet, and it orders the water molecules, even though they're free to move. And so water does have a, but look at copper 2 sulfate pentahydrate. That has a fairly high entropy. Why? It's because of these waters here. Waters being incorporated in there. Because if we look at just plain copper 2 sulfate anhydrous, it's going to have a much lower entropy than the hydrated form. All right, so are we good with this? So we have some ideas of the entropy values. What we want to do is we want to kind of associate with the numbers with some kind of visual idea of how ordered these things are or disordered. So if somebody said, "Oh, I just calculated the entropy of that solid. That entropy is 5,000 joules per mole Kelvin," what would you say? Wow, that sounds way out there, right? Way out there. It's funny because in Chem 1A we have the molar mass of the acid, and I have people who've turned in Chem 1A reports that say the molar mass of that acid was 1 times 10 to the minus 8 grams per mole. 1 times 10 to the minus 8 grams per mole. Unbelievable. Because even hydrogen's 1 gram per mole, so that's a very special acid. Yeah, those are always fun to see. Just people way out in space, drifting. Anyway, let's get back to this. So what you want to do is kind of familiarize yourself with the numbers. Now, these negative ones, for the cations, we could. It's the same thing here. If the entropy of H plus was 0, then if you measured for HCl, when we form HCl, we get H plus and Cl minus. So when you look at this, if I'm looking at the entropy of HCl, it's 56.5. Of that 56.5 is all chloride, and hydrogen is 0. That's a huge error. Isn't that a huge error? That is an enormous error, because hydrogen ions can't be 0. And so how can we live with such a huge error?
That's under a arbitrary solution.
Well, yeah, we know, but this error is self-canceling. One entropy is going to be too big, the other entropy is going to be too small, and when you add them up, the errors cancel each other out, right? You can't form a cation without an anion, so the errors are going to cancel each other out. And once we do that, then this is the correct entropy, because the correct entropy was 56.5. Let's go take a look at chlorine's entropy. Chlorine's entropy should be 56.5. Chloride, I should say, is 56.5, right? Uh-huh.
Isn't H plus just a proton? So how can it have any entropy?
H plus is abbreviation for hydronium. I'm just going to use it. A lone proton is too reactive. A lone proton is not. Okay. But even if it were a lone proton, the entropy would be in space. In space, what you have to do is you have to restrict that to one point in space. Is it restricted to one point in space? No, all of a sudden there could be a whole bunch of disorder. If it were perfectly ordered, then it's always in that one spot, and we can always find it. It's there because it's everything's perfectly ordered. But once you start introducing, well, that proton might be over there, or it might be over here, or it might be here, then you introduce disorder. All right. And so calculating entropies is very easy. How do we calculate entropy changes? Actually, calculating entropies isn't so easy, but we have a table, and the table shows us the entropies here. Calculating entropy changes is very easy, because all we do is this. Delta S is equal to S final. So sum up all the product entropies and subtract that from all the reactant entropies. Oh, it depends if you're going left to right. So just final minus initial. The entropies are extensive. What does extensive mean? Energies are extensive. This is back Chem 4, Chem 1A beginning. Extensive versus intensive properties. What's the difference between an extensive property and an intensive property?
Expensive is like color.
Could be. Now, color is debatable because certain colors are intensive, certain colors might be extensive. A lot of people say colors are intensive.
Extensive properties depend on
Amount, right? Extensive properties depend on them. And so if you had 2 moles of chloride, rather than, actually this is, you'd have to double the entropy, right? If you have twice as much, you're going to have twice as many ways to range. It means the entropy should be twice as much. So these entropies are per mole of substance, per mole. Here. All right, now what we can do is we can be more quantitative in determining the energies and entropies.
You said that the entropy would double if you had twice the amount, but moles is under, or is it's 1 over moles. So if you did twice the amount of moles, wouldn't it half?
Well, let's say the entropy were 56.5 joules per mole Kelvin. And so if you have 2 moles, then you want the moles to cancel out. This is something I noticed on the test. A lot of people didn't write any units, and got it wrong. Some of the stuff. If they had written units, they probably wouldn't have written the same equation. And so that's like a Chem 4 mistake. You don't want to get in that habit of, only rookies don't write units. All professional scientists are going to be writing their units out. And so make sure you write your units out. Otherwise, you aren't going to get that far before somebody's going to say, something. And so not only do you want to write out the units, because, some people were, if you had the 2 moles on the bottom, then that would give you moles squared on the bottom. Is moles squared a sensible unit? No. And so it has to go on the top. And so it would be double. What was it? Yeah, it was this. Well, there were a lot of other screw-ups too. But for example, 1 mole of ammonium per, 1 mole of ammonium sulfate for 2 moles of ammonium. So you don't want to be caught, by something like this, because this should be Chem 4, Chem 1A. But a lot of people didn't even have anything. And then some people were doing some conversions like this. Ammonia and ammonium, are they the same? No, totally different. So a 1-to-1 mole ratio of ammonia to ammonium means your buffer. But anyway, just make sure you do that. I know we skip units so much because of the K's, the equilibrium constants. We got really lax on the units because the units for those are activities, not molarities, not atmospheres, but activities. Activities are dimensionless. And so this is why. And then we're substituting molarities instead of activities because we don't want to do all that stuff, compensate for non-ideal behavior, right? But it's obviously we're introducing error into the calculation. But that error, it depends on what you're looking at, because some things behave more ideally than other things. So sometimes the error is minimal, sometimes the error is very large. Now, for this chapter, we have to be very careful about units. We also have to be very careful about sign convention. You guys remember system surrounding sign convention? System, negative 10 joules. What just happened? Systems, negative 10 joules. What just happened? Okay, system lost 10 joules. Surroundings would be? And what would surroundings be? Plus 10 joules. Good. So we're going to keep track of all the signs again, and to make sure we're looking at everything from the system's point of view, but not always. Sometimes we'll look at the surroundings point of view as well. So let's take a look at some calculations here. Oops, wrong chapter. Some of these problems we don't have the data, so take a look. Okay, we'll do something simple here first. 77. Oxides of nitrogen are produced in high temperature combustion processes. Normally, like the nitrogen and oxygen, that forms a pretty stable mixture. Air, do you worry much about the nitrogen reacting with the oxygen in the air? No. Fairly unreactive. But at high temperature and at high pressure, they can react. And so all we're going to do is we're going to figure out what delta H for this is and what delta S for this is. And so let's go. We aren't going to do the whole problem because we've got to do more in order to complete it. But if we're looking at this reaction, nitrogen plus oxygen gas goes to 2NO gas. The state's very important because the state will influence delta H and the state will influence delta S as well. Let's go ahead and calculate delta H. Delta H for this reaction is, well, typically when you think about a combustion reactions, most combustion reactions are exothermic combustion. We're just oxidizing this with O2. So we're trying to burn the nitrogen in O2. Nitrogen's not very flammable, is it? No, nitrogen's pretty inert. And so what would you guess, exothermic or endothermic? Well, typically when we oxidize things, it's a exothermic. So how many people think endothermic? How many people think endothermic? Exothermic? Okay, let's take a look at the data. In order to figure out what it is, it's going to be nitrogen. Okay. From my book. N. Okay, here we go. NO. And so we look at delta H of formation for NO. And so the easiest way to do this is by delta H of formation. So delta H of formation of NO, we got 2 moles of that. And so this is going to be 2 times 90.25. Units, kilojoules per mole. But we have 2 moles, so the moles cancel each other out and leaves us with kilojoules. You should know the delta H of formation of nitrogen. What is the delta H of formation for nitrogen? 0, and the delta H of formation for oxygen is 0. So both of those are 0. So products minus the reactants, 0 plus 0, which is going to give us 180.5 kilojoules per mole. Positive. Kilojoules for the reaction is written. This reaction is written as 2 moles of NO, which is double that information. Thanks. 180.5 kilojoules plus, which means it's endothermic. And so this one turned out to be endothermic. It's not like if you tried to burn or combust a brick, is that going to be endothermic or exothermic? Like a brick. That'll probably be endothermic, you know. It's not going to burn. So it's the same thing with nitrogen, it's too stable. So it turns out, yes, it is. But typically, you know, when we combust things and they're flammable and they spontaneously combust, then we normally think of it as being an exothermic process, giving off heat. This is endothermic process. So far, this says nitrogen shouldn't burn because entropy. Now let's go ahead and get the entropys for this. So delta S for this reaction. Oh, this is under this. What does this little 0 mean again?
Standard.
Okay, standard thermodynamic conditions means what?
1 bar.
1 bar or 1 ATM.
There's no standard temperature.
There's no standard temperature, right? That little thing doesn't tell us the temperature. What else does it tell us, though? It should be 1 bar, 1 ATM, and 1 molar. The temperature we usually write down here, this is going to be at 298 Kelvin. If we change the temperature, then we need another data table, don't we? Which we don't have, but you can find them. So this is going to be the standard 298 Kelvin. There's one other thing about the standard. Since the pressure is specified, that means all these are under constant pressure or constant volume? Constant pressure conditions. And so delta S naught of the reaction is just going to be the entropy of the product. So we got 2 moles of product. So we got to figure out what the entropy of NO is. Entropy of NO is 210.8. Take a look at these 2 gases, though, the illustrative point. NO is 210.8, N2O is 219. So would you expect N2O to have a higher entropy than NO? Yes, because it has 3 atoms versus 2 atoms. So 3 atoms, but they're both gases. So the most important factor is the gas. Adding that extra atom doesn't really increase its entropy all that much, right? It just has more vibrations. That's about it. But you know, the gases can be anywhere in space. It's mostly empty space, so that makes it very unconstrained. You know, the more constrained, the lower the entropy. And so here, 2 times 210.8 joules per mole Kelvin. Now this is 2 moles. All right. And so I should be paying attention to my little spiel about units as well. What about the entropy of N2? Is the entropy of N2 0? No. The entropy of N2 is not 0. What about the entropy of H2? Is the entropy of H2 0? The entropy of H2 is positive or negative? What about the entropy of H plus? Yeah, arbitrary 0. Okay, you got it. The entropy of N2 is not 0. The entropy of N2 is 191.6. So this is the entropy of the reactants minus the entropy of the products. 191.6 joules. We only have 1 mole of it, so I'm just going to go ahead and cancel that out right now. And the entropy of O2, element O, is not 0. Entropy of O2 is 205.1. Joules per Kelvin. So what's happening with the entropy here? is negative?
24.9.
Positive?
Yeah.
Positive 24.9 joules per Kelvin.
So the enthalpy says reaction or no reaction? Enthalpy says, well, enthalpy. Enthalpy says no reaction. Entropy says reaction. So which one wins? Is it a tie? Well, we know which one wins at 298. Which one wins at 298? Enthalpy wins because there's no reaction between nitrogen and oxygen at room temperature. And so what we do is we got to figure out how do we compare these two numbers. Well, one, they're in different units, right? So it's hard to compare things with different units. How do you get them to the same unit? Well, to get to the same units, I'd have to convert joules to kilojoules, and I have to get rid of the temperature, the Kelvin. How can I get rid of the Kelvin? Maybe if I multiply it by the temperature, 290 Kelvin, I can get rid of that, convert it to kilojoules, and then compare those directly. Do you think that works? And so we have to figure out a way. And so what is the criteria for reaction or no reaction? And so sometimes, how do we weigh these things? And so we got to look for something, some solid rule or a pattern that says, whenever we have this, a reaction will occur or not occur. And so that brings us to the second law of thermodynamics. All spontaneous reactions must meet this criteria. All spontaneous reactions have delta S of the universe greater than 0. And so if you look at all the spontaneous reactions, one thing that they all share is that the entropy of the universe increases. The entropy of the universe, delta S of the universe, is equal to delta S of the system plus delta S of the surroundings. We can measure delta S of the system quite easily because we just did, right? The system, it's a reaction there. But what about delta S of the surroundings? How easy is that to measure? This is easy because we have appendix D. This looks hard because that's everything else in the universe. And so what's going on with everything else in the universe? And so how do we deal with that? Do you want to see a video on this? I'm going to show a video. Let me pause this.